Okay, so let me start. Good afternoon, and thank you for coming. My name is Doboš. I'm a solutions architect with Canonical, the company behind Ubuntu Linux distribution. And today I will discuss with you what are the solutions we are bringing to you, which are now running also on PPC64 LE architecture. So you can use them to build and operate your private and hybrid clouds. So before going to the technology, let's just mention where we are in terms of Ubuntu, Canonical, and OpenPOWER Foundation. So I work for a company Canonical, and we are the platinum sponsor of OpenPOWER Foundation. And our major open project is Ubuntu, obviously, the Linux distribution. So a bit about history. In April 2014, the Ubuntu 14.04 came to the market, supporting not only x86 and ARM, but now also IBM Power architecture. 14.04, as you see, is marked as LTS. LTS means a long-term support, which is our Ubuntu release, which will be supported for 5 years and more. As you might know, our roadmap, every 6 months there is a new release of Ubuntu. All those releases are supported for 9 months, while the LTS versions are supported for 5 years and more. Every 6 months on the same date, that's the release parity, on the same date we have the new Ubuntu release available across hardware platforms. And we do support ARM, x86, Power architecture, and also S390X architecture. These are the scale-up IBM servers. So the upcoming 18.04 will be the one to support Power 9, while 14.04 does support Power 8. And it's not only Ubuntu, but our full software ecosystem we are bringing to Power. I'm saying our software ecosystem, all those are open source projects, besides one exception, which is Landscape. That's the management tool. It's what you might know, Red Hat Satellite or SUSE Manager. So this is our tool for managing your servers. Otherwise, all the other pieces here are 100% open source. Some of the projects are led by Canonical, but all of them are open source, and everybody is welcome to the party to contribute. I think it's also worth to mention our model of doing business is that we don't have licensed products. All the software is free, and the commercial support is optional component. So you can, but you don't need to go with commercial support from us. So actually, this one is kind of the summary of all the cloud and containers related projects we believe in. And let me now start from the most important part for this discussion, which is the bare metal support. So what we do in terms of supporting the Power servers. I will just say Power servers. By that I mean, obviously, products from different vendors, but based on Power architecture. So there is a project called MAS, Metal as a Service. You see mas.io is the homepage of the project. And from the administrator of the machines, what it does. So without the tool like this, what do you have to do if you have a new server? You put it on your data center, you plug it to your infrastructure in terms of electricity and networking, maybe external storage if there is some. And then in some way you have to provision operating system into it. Right? In the old times we came with the CD. Now it's maybe USB stick, or you just Pixie boot it somehow. You configure your network in terms of DHCP DNS. And then you take care about that server, and maybe from time to time you update some patches, and maybe from time to time you have to rebuild the server again. So this is what can be fully automated by using MAS. So this is what MAS is doing for administrators, helping you with the management of the servers. And then users of MAS can consider MAS as a bare metal API. So as you have APIs to your Amazon or any other public cloud provider, you have also now available APIs to work with your on-prem hardware infrastructure through MAS interfaces. So this is the real issue when we compare our on-prem with public clouds. How long it's going to take to instantiate a new instance in the public cloud? How you do that? Knowing the interfaces, you do it with a piece of script, and it will take you several minutes to have your new server in public cloud up and running, right? And now we can discuss if this X is 2 minutes or 5 minutes, but we definitely know it's in several minutes. How long is it going to take you on your on-prem infrastructure? If we would consider the end-to-end cycle, starting with the request through procurement till the physical installation and deployment of operating system, it maybe still will be X, but definitely not minutes. Maybe hours, days, weeks, months, depends of your organization. So this is what Mass is bringing in the game to shrinking the time using the automation. Of course, Mass will not help you to speed up your procurement cycle. The point here is to operate your on-prem infrastructure with the efficiency of public cloud, maybe to repurpose the server as you need automatically and so on. So in ideal world, you will see your server only once when you plug it on the floor or in the rack. Otherwise, you do everything with tools like Mass. So these are the several steps through that life cycle. Let me drive you through some screenshots. I'm not going to do the live demo. I was asked better not to do it because of networking potential issues. But let's at least drive you through the major steps here. So Mass does have a concept of high availability built in. For that, we have the high available concept of region controllers. And the region controller can talk to several rack controllers. So on each rack, you normally would run one rack controller. Ideally, maybe in the top of the rack switch. There are already some devices available on the market running Mass inside top of the rack switch. And then that rack controller is managing the nodes inside that rack. So you see that the copy of images you would potentially like to deploy to those nodes, and we will discuss those images, where they are coming from and how you can build your own image if needed. Those images would reside in the rack controller, while region controller will provide the services of DNS, network time, syslog, and proxy, and so on. So that's the high-level concept. Then, in the end, Mass should, when you use Mass, you will inform Mass about all your servers and your networking configuration. So here is an example of two fabrics with on each there are no VLANs activated, and there are several subnets there. So this way you have the inventory of your servers and networks in one tool, and then you can instruct Mass that each time you would deploy an operating system to the particular server, you can influence to which network that server will be connected. So Mass can do it automatically for you. So this is what, when configuring a specific node, here on this example, you see there are several networking interfaces. And as you see, we do not deal only with physical networking interfaces, but we also support the Linux networking concepts like bridges and bonds. So you can instruct Mass that every time the operating system would be deployed, a bond or a bridge will be created inside that operating system. So that was a bit about networking, and of course we do support the protocols like DHCP, or you can instruct Mass to assign the IP addresses based on some internal algorithm not to use DHCP. You can statically allocate IP addresses. You can inform Mass about the other devices you have on the network, like routers, switches. So Mass would never allocate that particular IP address to one of the nodes. This is and the next step is about allocating the disk space to the nodes. Again, when you put the new node in the rack, based on the type of the node, Mass will either sense it, or you will manually instruct Mass to put some information in Mass about what is this server about, in terms of what kind of BMC it is and IP address on which the BMC is running. And then MAS will run kind of inventory of that server, commissioning. So after that process, MAS will fully understand what is the hardware about, not only in terms of cores and memory, but also in terms of networking interfaces and disks inside. So MAS now have the info about the node, and you can create your partitioning scheme of your disks here. So when the operating system will be deployed, the correct scheme would be applied immediately. So this is an example of the screen where I see that I have already some nodes, node 1, 2, and 3, 1 and 2 running Ubuntu. So these were already successfully deployed. Node number 3 just deploying CentOS 7. And node 4 and 5, node 4 is there, ready, waiting. And node 5 is just testing itself. So there is a set of script of MAS, so you can just say, test yourself to check that the hardware is still okay, that it's in the good health conditions, ready for an operating system to be deployed to. So the question now is what kind of operating systems we could deploy with MAS. So out of the box, we do support Ubuntu releases and CentOS. This is what is coming out of the box. So without any commercial support from Canonical, Ubuntu and CentOS can be deployed. Then we're ready to help you to build the Red Hat and SUSE images and Windows images for x86. But of course, these are licensed products. So for that, we cannot just do it out of the box. You have to provide us with some proof of the license and license number and so on. So we can help you to build those images. And some clients are interested in the custom images. So that could be, for example, a specific Red Hat image with some middleware inside already. So every time they deploy not only the server itself, but also with some pre-tested, preloaded applications. So for custom images and non-CentOS and Ubuntu images, you would need to go in the commercial agreement with Canonical. And we would provide you with the tooling for creating those images. So imagine my MAS is already up and running, having all the information about my servers and networking. So now I can really using those APIs mentioned at the beginning. This is now my bare metal cloud. So I can now make calls to the cloud like it was a public cloud, saying, find me a machine with these characteristics. Here in my example, it's find me a machine which is of the hardware architecture PPC64, so power architecture. Find me a node somewhere where there are GPUs inside, and this size of the memory and so on. And if you find such a node, now deploy a specific operating system in that from those images which are there in MAS. So this is what MAS is doing. So how I can do it? I can do it from a MAS GUI. I can do it from command line with MAS command. So this means also I can do it from any kind of scripting language. So that's that CLI option. But I can also use some tools which are available on the market, which are able to consume those interfaces like Chef. Some clients are using Ansible for deploying their stuff on top of MAS Cloud. And we also provide another open source software called Juju, which I will introduce to you soon. So then, once I build my MAS bare metal cloud, to me, it's now the same concept as dealing with public cloud. With a piece of script, I can call my cloud asking, give me an instance with the specific parameters, with a specific operating system. Okay, so that would be a bit kind of introduction to MAS. Again, mas.io. It's the webpage where you can find more information. Again, 100% open source project, free to use cross hardware architectures. So now let me move to other piece of technology, which later I will show you how we use it in building OpenStack from Canonical. And this is a piece of technology called LXD, which we introduced as a fully supported option with Ubuntu 16.04, so in April 2016. So what is LXD? So first of all, let's talk about LXC. What is LXC? So as you might know, LXC is an abbreviation of Linux containers, a technology which was born at IBM some years ago, probably as an answer to Solaris Zones, which was the containers technology on Solaris operating system. So it's a pretty cool technology, and if you are familiar with Docker, which is kind of de facto standard for applications in containers as of today, the first Docker was based on LXC technology. So Docker was actually kind of the way how you can consume LXC technology in the nice way. So we offering another way how you can consume LXC technology. It's called LXD. Consider LXD as a LXC version 2, with D being the daemon. So it's kind of wrapper around LXC technology, giving you another experience how you can consume containers. So from the very high level, what is LXD? So imagine LXD being a kind of hypervisor, in quotes, providing you not with virtual machines, but with containers. But those containers behave like virtual machines. So from your perspective, from user experience, every time I will say, hey, LXD, give me one more container, type of Ubuntu or type of Debian, I will have an impression I got a full virtual machine, even if it's container, but I will have an impression it's a virtual machine, and I can use standard ways how to install some software inside that server. So with Ubuntu, I can just use apt install command. With CentOS, that would be yum install whatever it is. So it's a full machine kind of container. Any questions so far to that LXD? Because can be a bit confusing because people really now having Docker in mind when we're talking containers. So let me explain it a bit better on this chart. So on this chart, I got 5 Ubuntu hosts, A to A, B, C, D, whatever, maybe E. Each of those is, of course, running Linux kernel, and each of those is running also the LXD daemon. And then each of those is running several LXC machine containers here on this example. How I can instantiate those containers? So for that, we have a LXD REST API. So again, I have my CLI, so I can use it through my scripts, and I can just say LXC launch Ubuntu 16.04 container 1 as a name, and in 2 seconds I have a new server running on my system. Of course, as a virtual machine, or technically it's a LXC container. The other option how I can do this is through OpenStack. So as you might know that KVM is the de facto standard for OpenStack hypervisors. We provide drivers for LXD, so there is a Nova LXD driver. So you can say that on the particular node, like here, node B, host B, if it was a node in my OpenStack, I can just say, give me a new instance on that node, and it will not be a full KVM VM, but it would be a LXD. So I can, of course, then in one OpenStack, I can combine those 2 technologies. So some nodes can be running the KVM hypervisors, and the other set of nodes are LXD hypervisors. So what would be the big benefit of LXD comparing to KVM? The biggest advantage here is the density. Because as you see, on each node, I'm running just one kernel. So all the other containers are sharing the same kernel. While with KVM, if I had 10 virtual machines, it would mean I'm running 11 kernels of my node. A kernel of my host plus 10 kernels, 1 per each virtual machine. So in fact, as I said, LXC means Linux containers, so definitely you cannot run Windows like that. But I did not say it's Ubuntu containers, it's Linux containers. So I can run CentOS version 6 in my LXC containers, fully leveraging the newest Ubuntu kernel of the host. Okay, so I can combine different Linux distributions under LXD. So actually, we as Canonical, we are maintaining those images for LXD. Again, in general, that is a pretty long list of images for different Linux distributions, specifically on Power. We do support Debian and Ubuntu images as of now for LXD. For commercial support, of course, we can build also images for other distros if there is such a request. So density was the biggest advantage. The other is, I would call it close to bare metal performance, because actually each container, as you can imagine, is implemented as a process on the kernel. So there is no latency like there is one with virtual machines. So those Linux containers are leveraging the latest Linux kernel technologies like namespaces, C groups, and AppArmor. That's the combination of those three, giving you the isolation between containers. So don't take me wrong, LXD is not meant to be a replacement of KVM, because maybe some clients for some specific workloads still need to have the isolation which would be provided only on virtual machine level. But for other workloads, maybe LXD, Linux containers, is good enough isolation for plenty of workloads and plenty of situations. So that would then give you the option to squeeze your hardware better. Based on x86 benchmarks, we have 14 times better density with LXD comparing to KVM, so it's really significant. You remember this morning, we were told, during the keynotes, we were told that there is an issue that, okay, you can do the virtualization only once, and then you already have the benefit, but it's difficult to find another zero, how you can make your utilization of hardware even better. So give a try to LXD to compare it with your KVM, if you're running KVM, and maybe this can give you additional benefits of virtualization. And in April, so what I was mentioning is true since April 16. In April this year, we will bring to the market the LXD clustering capability, which then means that you can just call, here in this example, I put my 5 nodes in one LXD cluster, and then I can make the call like, hey, LXD, give me an instance, or I need 2 more Ubuntu instances. So somewhere in that cluster, those instances would be created. Of course, I can still have the option of explicit placement, and I could say, give me 2 instances of CentOS 7 on host B. So as a summary of LXD benefits for cloud, very easy way how you can lift and shift your existing applications without building Docker images and changing your processes, how you deal with applications. So if your applications are happy today in a VM, they should be also happy inside an LXD container with LXD. Then this is also the way how we can collocate different components of different, if I have a software solution, which is pretty complex, having different components, I can easily collocate them on the same physical node while having the isolation provided for LXD containers by LXD. And then I give you an example of our OpenStack, how we deal with that. And LXD in general can also give you some benefits in any kind of cloud, because typically in public cloud, you have your instances implemented as virtual machines. Nobody can stop you if you have a Ubuntu virtual machine instance in cloud to enable their LXD inside and put some more workloads inside that instance. So let's move now to another project of us called Juju, which we consider to be the model-driven operation of the software. Is anybody familiar a bit, at least, with Juju? Okay, thank you. So first, let me do some high-level messages here. What Juju is doing, Juju is helping you to deploy and operate software in clouds. Okay, so Juju has this concept of charms, where charm is technically it's a collection of scripts. So we providing some framework, and every single software project can have a Juju charm for that solution. So we have Juju charms available for OpenStack components, for MariaDB, Postgre. Actually, these are hundreds of charms available in Juju charm. Just check jujucharms.com. these are, again, it's kind of open source operations. So not only you have open source software for free, but also the way how you would operate and deploy. And by operation, I mean all these actions: installation, configuration, scaling up, scaling down, health checks, typical application, potentially for a database, the typical operation can be backup, restore, upgrade. So all of those are encapsulated inside charms. And then I have besides my command line, I have also my GUI where I can model my solution. And here is a very simple solution. It's for WordPress. So as you see, there is a WordPress charm in the middle. There is AJ proxy on top. And there is MySQL to host the data of that WordPress. So all I need to do is to put those bubbles on my canvas, draw the line between A and B to build a relation, because Juju charms, they have also the information encapsulated about how to integrate with other pieces of software. And once I build this, I can just say how many instances of those I'd like to have. This is my model. And now I can deploy this model to different clouds. So of course, all the major public clouds are supported. But here specifically for this event, what is important, MAS is supported as one of the substrates where Juju can seed the applications. So MAS is fully supported as a bare metal. So actually, everything you can do with Juju and MAS on x86, now you can, and in public cloud, now you can do also on Power-based servers. And we do same also, of course, on x86 and on the other architectures we do support. So that's the concept of Juju, to give you the option to deploy applications on top of clouds, and MAS being one of the clouds we do support with Juju. So of course, there I could not run the session about building cloud on Power with Ubuntu without mentioning OpenStack, because actually OpenStack and VMware are the two options how to operate or how to build your private cloud. So we, as open source company, of course, we believe in OpenStack. We're one of the first members of OpenStack Foundation. So this is just to ensure you that all we do in terms of OpenStack, we also do on IBM Power. So it's easy now with MAS, Juju, and our OpenStack to build your OpenStack cross platforms, again, including Power. I was already mentioning Ubuntu release cycle. And you know that OpenStack also had the same cycle 2 times a year. So we have the same concept of OpenStack LTS versions. So every 2 years we have a LTS version of OpenStack, which we would support for 5 years, sometimes even more. The other versions of OpenStack we do support for 18 months, and every other we support for double time of that for 3 years, for 36 months. So we have very predictable roadmap in terms of Ubuntu server and OpenStack. I was already mentioning that we are using LXD heavily for our OpenStack. So this is an example of an OpenStack architecture. And you know that OpenStack is organized in different projects, a lot of components. And here on this architecture, you see that some of those are here implemented on bare metal level, like the hypervisors, you know, Nova KVM and Nova LXD, and Ceph and Swift right there. Some of them are implemented as virtual machines, and plenty of them here are implemented as Linux containers under LXD control. Again, this is an example. With Juju, you can model your OpenStack deployment for your needs and then just ask Juju to deploy that model to your bare metal hardware infrastructure. So that would be the model of OpenStack then. And so that was OpenStack for infrastructure as a service. As you see what's happening on the market in terms of containers, Kubernetes really has a big momentum there in terms of coordinating Docker-like containers, the containers having applications inside. So we also fully support canonical distribution of Kubernetes on Power. And canonical distribution of Kubernetes is 100% upstream Kubernetes and deployed and operated with Juju. So the same way you can deploy your OpenStack on top of MAS, you can also deploy your Kubernetes cluster either on top of MAS or on top of OpenStack if you like to deploy Kubernetes on top in virtual machines on OpenStack and not on bare metal. So to conclude the session, here are some articles where we're describing how we deal with LXD, NVIDIA GPUs, how we commoditize GPUs with Kubernetes in general, which could then go even to kind of commoditization of AI technologies. So I can then, Juju deploy Kubernetes and on top of that use maybe Helm to deploy my TensorFlow framework. So again, it's a cross-hardware architecture story. Whatever we do it cross-platforms to give you the same experience. So you don't need to invest heavily in the new knowledge of specific architectures. So as a summary, yeah, Ubuntu pretty successful in clouds. Keep in mind that whatever we do also on Power architecture. So if you go with Ubuntu, you can keep your strategy easy, that your hardware architectures would be covered all. So that would be from me. Thank you very much.